Hello and welcome to today's lesson. What we're going to do today is we're going to do some work with the graphing calculator. So if you have your own graphing calculator, you want to take that out and have it ready. And if you don't have your own graphing calculator, you can use the instructions that I posted in Google Classroom to go to the PARC website, the NJSLA website. And the instructions are there for how to get to the graphing calculator. And you can do everything you want to do with the graphing calculator right on this one. So what we're going to do is work in section 3.2 to start if you're in Precalc. This is section 6.3 if you're in Algebra 2. And the first thing we want to do is evaluate some logs. So first thing is log of 42. And to evaluate the log of 42, you just want to use your log base 10 button. So this is log base 10 because there's no base written. And when we get to number 2, that's natural log base E, because it's ln. Those two buttons are built into the calculator. So if you look to the left of 7, you see log. That's specifically for log base 10, the common log. Next to the 4 is ln. That's specifically for natural log. Okay? So if you want to find the log of 42, you just hit log, the button next to the 7, and you put 42 and you hit enter. So the log of 42 is about 1.6232 if we round to 4 decimal places. And you'll find that we often round to more decimal places than normal because usually we round to like 1 or 2 decimal places. But since we're finding an exponent, we're going to round further because exponents are very powerful. And just to show you what I mean real quick, if we just think about what this is log base 10 of 42 equals what number? So we're finding 10 to some power that gives you 42. So if I want to check this in my calculator, I can do 10 to the 1.6232 power, and I'm going to get pretty close to 42. It's not exact because this is an approximation. We rounded to get this, but we're going to get very close to 42. If we only rounded to 1 decimal place like we're kind of used to, what would happen here is we would have used just 1.6, and we're not very close to 42 at all. So exponents are very powerful. They have a big impact on a number. So that's why in this unit, we're going to round out further than normal. Okay, and if you want to find the natural log of 15, hit natural log. That's the button next to the 4. Plug in 15 and hit enter. So nothing fancy to do when you want to evaluate common log or natural log. And rounding to 4 decimal places, just remember, since this is a 5, we're going to round this up to a 1. Okay, the next one is this. So if you printed out the handout, you can just follow along. If you didn't print out the handout, you want to write these down in your notebook. So just pause as needed and write them down, and then we'll get them in the calculator. So for this one, we're just going to type in what we see. So we're going to type in 2 times the common log. This is log base 10. So I just use the log button of 7. And what's important here is before we continue in the calculator, we have to close the parentheses. Because the only thing we're taking the log of is the 7. Even though they weren't written, that's the only thing that's inside the log. Then we have plus e to the 4th and a minus 1. So for e, you can do second divide. So if you forgot where that button was, it's second divide. Or you can do second ln. If you do second ln, so here's second and ln. You'll get your e. So I used second divide, but if I were to use second ln, it would set me up with the exponent. And I want to the 4th power, and then I want to subtract 1. So we have 55.2883 for that. And if you have a slightly older graphing calculator, it's going to look like this. Because when I did e to that power, it doesn't actually show the exponent raised up. It just puts that caret, and then whatever's in these parentheses is going to be what the e is raised to. So once again, make sure you close those parentheses before you put that minus 1, because if you don't close the parentheses, you're going to get a wrong answer. Okay? And then just for those of you who have the newer graphing calculator, just to show you, you have 2 log of 7. You also have to close the parentheses before you go ahead and do e to the power. But your calculator, if you have a newer one, or if you're using the online one, it actually raises the exponent up there. So before you put that minus 1, you want to get out of the exponent. So just use your right arrow button. Your right arrow is this guy here. And then you can put your minus 1. And you get the answer we got before. All right, so that's evaluating logs and the a base of E. And we can also graph on the calculator. So just to quickly kind of show you that, I have, let me graph common log. So here's common log. I'm going to go to Zoom Standard. So this is log base 10. And you can see that the calculator, it shows me a good part of the graph, but it's missing the part that comes down toward the asymptote. You might not even notice it if you're using a calculator that doesn't have the color graphing. So if I show you on the other calculator, log of x, you might not even notice that the calculator is not putting that part that comes down toward the vertical asymptote. But if you have a color graphing calculator, you'll notice it. It's just a limitation of the calculator. What's happening here is as we get closer to the vertical asymptote, the calculator, this graph becomes so steep that the calculator really can't graph it properly. So it kind of gives up in a sense and stops graphing. And it's just, again, a limitation of the calculator that you want to be aware of. Because even if this is the graph you're looking at, what the graph of the common log really looks like is this. So even though the graph looks like this on the calculator, if you were going to sketch it, you would sketch it properly the way that you know it's supposed to graph. Okay. And then you can also do transformations. So if I wanted to move this, for example, up 2, I can throw a +2 outside of the parentheses. And you can really see the calculator's limitations here if I do the horizontal shift. So let me move that 3 which way? To the right. Yep. So if I move that 3 to the right and up 2, it looks like this. And that's really not what the graph looks like. What the graph should look like is it should have gone 3 to the right, moving the asymptote to 3 and the intercept to 1, and then up 2. So the graph really should look like this. It should not chop off at the end there. So even though the calculator shows it kind of incorrectly, make sure that if you were to sketch it, you sketch it properly. Okay, so continuing on, we've evaluated common log and natural log. The next thing we want to do is evaluate log with other bases. So this part's going to take a couple minutes because depending on the calculator you're using, there's 3 different things that can happen. So I have to show all of them right now. And I'd have to do this in class if we were in class as well. So here's the example we're going to do for log base 4 of 17. And if you think about that for a minute, you should be able to get some idea of what the answer will be. Because what you're solving here is 4 to what power is 17. So since 4 squared is 16, we're expecting an answer just a little bit bigger than 2. We should get an answer a little bit bigger than 2. Okay, so here's what may happen when we try to do this in our calculator. So if you have a newer graphing calculator or you're using the online calculator, if you click Math, that's this button right here. And then as it says, scroll down past 9, 8, 9, there we go. If you scroll down past 9, past 0 to A, log base, and some of your calculators won't have this, so don't panic if you don't see it. We'll get to your calculators in a minute. But we have that log base there. So if we hit enter, we can plug in exactly what we want. So we can plug in a base of 4 and 17 for the input for the log. And there's the 2 points, just a little bigger than 2 that we were expecting. So 2.0437 if we round to 4 decimal places. So if you're lucky enough that your calculator has that feature, you can just pop that right in. Another possibility with your calculators, just to show you another thing that can happen, this is the least common, but when you hit Math, so I hit Math and I scroll down past 9, past 0 to A. If you have a slightly older calculator, you might get this where it says log base. Okay, so if it says log base, here's what you do. You put your input and then a comma and then the base. So if we want log base 4 of 17, what we will do is put 17, a comma. Comma is on the calculator right above a 7, right there. Okay, so I put the input, what we're taking the log of, and then the base. and that'll give me the same answer that I had before. And then there's a third possibility. If you're working with a slightly older graphing calculator, when you go to hit math, and then you go to scroll down past 9, past 0, you don't have that feature at all. It just doesn't say log base at all. So if you have an older calculator, you just don't have that feature. I would not go out and buy a new calculator for that. Even if you're going to go and take calculus and beyond, you're fine. You don't need a new calculator. So I'm going to teach you a formula in a minute that you can use, and everyone's going to have to learn it. So don't feel like, like you're doing extra work or something. Or you can always go to the online graphing calculator I showed you because it has this feature. So those are the options that you'll have. Okay, so let's get to that formula next. And in your textbooks, here's the section if you're pre-calc, here's the section if you're algebra 2. And this is called the change of base formula. And even if your calculator has the fancy log base feature, you have to learn this. It's part of our curriculum, so everyone has to learn it. And here's how the formula works. What the formula allows us to do is if we have a log and we don't like the base. So if I have log base A here and I don't like base A, I want a different base, I can change the base. The way that I do that is I make a log with a new base. So in this case, I selected B. And what was inside the log goes inside the log up top. And what the old base was goes below. So the way that I remember that is the base belongs below. That's alliteration for you. So the base belongs below will help you remember that the old base goes on the bottom. So to understand it, you need to see a couple of examples. So let's take a peek at this one. So if we want to evaluate log base 4 of 17 using this change of base formula, either because our calculator doesn't have the fancy feature or because we all have to learn this formula anyway, what we can do is we can change the base. And the base we want to pick is one that's built into the calculator. The calculator has log base 10 and it has natural log. So those are the ones that you want to choose from. So we pick whichever one we want. I'm going to guess you like common log better, regular log. So what we do is we make a fraction. We use our base up top. Okay, so you do common log up top, common log on the bottom. So I'm using base 10 for these. What we are taking the log of goes inside. The old base goes inside the log on the bottom. So that's what we're looking at. That's the change of base formula using common log. And if we put that into our calculator, the common log of 17, close those parentheses before you divide by the common log of 4, we will get the same answer we had before to this problem. And the answer we had before to the problem was 2.0437. So it works. So I'm going to write that down here. And you can choose any base you want. So I think you guys probably like common log best. But we can do this with any base we want. So I could redo the same problem using a different base. So if I wanted to redo this using natural log, if I for some reason don't like base 4, I can pick a new base. I create a fraction with whatever log, whatever base I want, top and bottom. And what goes inside up top is whatever we were taking the log of. And what goes inside the log on the bottom is the old base. The base belongs on the bottom. And if I put that into my calculator, same answer. So you can do any base you want. The reason we pick base 10 or base E is because those are the ones that are built into the calculator. So technically, I mean, you could change them both to log base 3 if you wanted. So if you wanted to change this same problem using log base 3, you do log base 3 of 17 up top, log base 3 of 4 on the bottom. And if you were to do all the work to put that in your calculator, you get this anyway. But this is a lot of extra work. You wouldn't pick base 3. What you want to do with the change of base formula is pick natural log or pick common log. And again, that's because those are the ones that are built into the calculator. So this would give you the same answer, but you would never pick that. Okay. So one more thing just to note about this change of base formula. When you use the change of base formula, you probably like common log best, but I would encourage you to choose the natural log instead. because if you're proceeding to calculus, you don't do common log very often. It's natural log that you're going to see. So if you want to make a note that when you do this, choose the natural log. Because if you choose the natural log while you're learning this in pre-calc, then when you get to calc, you'll be more familiar with it and more comfortable with it. So let's continue. Okay. I know you just got one practice problem with that, but we'll practice that more in the next couple of days. What I'd like to do next is I'd like to get into some properties of logs and exponentials. And I'm not going to go through these with Algebra 2 because this is the first time they're seeing the topic. That would be a bit much. So, but for you guys who are reviewing this, let's talk about some properties. We're going to have 6 properties to talk about. So here's the first one. The first property says, if you have log with any base that's acceptable, so that base a, as long as a is greater than 0 and not equal to 1, good. Log with any acceptable base of 1 will be 0 every single time. So that's something good just to be aware of because it provides you with a shortcut. So no matter what the base is, if you have the log of 1, the answer is 0. So if you're working on a problem, you see log base 501, the answer is 0. This right here is common log. This is log with the base of 10. The answer is 0. Anytime you're taking the log of 1, the answer is 0. So that is a property and it makes for a nice shortcut. But just to let you know, you don't need to memorize it because if you ever forget or don't realize that you're looking at this property, you still know how to solve all of these. If you wanted to solve for log base 2 of 1 equals what, you would switch that over and say 2 to what power gives me 1? And the answer is 0. If you were trying to evaluate this log, if you didn't recognize that it's a property and you have a shortcut for it, no big deal. Because you can always just say, okay, this is 5 to what power gives me 1. This one would be 10 to what power gives me 1. And the answer is 0 for all of those. So it's a nice shortcut if you recognize it, but I wouldn't work hard to memorize it because you can always just rewrite it in the other form. Same with the next property. The next property says, if you are taking the log of something and your base and the input match, so if the base matches what's inside the log, the answer automatically is 1 every single time. So it's a nice shortcut because if the base matches what's inside the log, the answer is 1, like these here. Same with this one because natural log of e is log base e of e. So since the base and the input match, it's automatically 1. But you don't really need to memorize this because if you were ever doing work and you were trying to figure out what log base 3 of 3 is, you can just rearrange to the other form. So for log base 3 of 3, you'd say to yourself, okay, 3 to what power gives me 3? Well, what's that answer? The answer is 1. All right, so it's a nice shortcut if you recognize it. If the base and the input match, then you're going to get 1 as your answer. But you don't need to work real hard to memorize it because you can always switch to the other form. Okay, next properties. Those two kind of go together. The next properties, 3 and 4, also kind of go together. So these are called one-to-one properties. Number 3 and number 4 are one-to-one properties. Okay. All right, so one-to-one property. So here's what this says. If you have something raised to the x is equal to the same base raised to a different power, then that implies you can conclude that the exponents are equal to each other. It looks complicated, but I think you'll agree it's pretty simple. You've actually been using this already in the past. If you think back to problems that you've solved in the past, here we just solved one. We said 3 to what power equals 3 to the first. What was the answer for that question mark? It was 1. That's an example of applying this property. See how the bases match? So if the expressions are equal and the bases match, then the exponents have to match as well. You solved one like this in the past. You had like e to the second equals e to the x. Okay, so if e to the second equals e to the x, what does x have to be equal to? It has to be equal to 2. The only way these two are equivalent is if their exponents match. So even though it might have looked new and different, it's a property you've already been using. And I just wanted to establish that you are allowed to use it. It is an actual property. And it works the same with logs. So if you have 2 logs that are equal to each other with the same base, then that implies you can conclude that the 2 expressions inside are equal to each other. So where we're going to see this is like if we had an equation that said natural log of x equals natural log of 7. I don't think you need a property to solve this. If the natural log of x equals the natural log of 7, what is x? It has to be 7. Okay, so this property, even though it might look new and kind of weird, I think it is intuitive. I think if you were going to write the rule book, you would say, oh yeah, this makes sense. That does make sense. So here's another example. If you have log base 3 of 2 and that equals log base 3 of x, then what does x have to be? Then x has to be 2. And that property should make sense. And just to let you know why these are considered properties and why we bother to discuss them, it's because this idea does not work with every single function. So for example, let me show you a function that this doesn't work for. So you see y equals absolute value x. Here's my absolute value graph. If these two outputs are equal, so I'm using absolute value of x. If absolute value of x equals absolute value of 3, can you use the same idea we just used? Can you just assume that x had to be 3? If absolute value of x is equal to absolute value of 3, does x have to be 3? It does not, because what else could x have been? X could have been negative 3, we really don't know. So see this guy up here? He's not 1-to-1. Since this is not 1-to-1, it fails the horizontal line test. That's how we know it's not 1-to-1. If you know the output is 3, that doesn't guarantee what the input is. If the output is 3, does the input have to be 3? No, that input could have been negative 3 instead. There's no guarantee. So when your function's not 1-to-1, you can't make these types of conclusions. So what's special about your exponential functions, if we take an example, let's take the example of y equals 2 to the x. Okay, so 2 to the x looks like this. And it's 1-to-1 because it passes the horizontal line test. So let me just ask you this. If the output is 8, let's say we're getting out 8. Can you tell me for sure what the input was? It had to be 3, because the only way you're going to get out 8 here is if you do 2 to the third. That's the only way you're going to get it out 8. There's no other way to get that. So if you were working on a problem where you had 2 to what power, let me move that down. So if you were working on a problem, let me put it over here actually, and you have 2 to some power equals 2 to the third, because that's what 8 is, right? What does the x have to be? It has to be 3. So if you know the output, it's guaranteed you can figure out what the input is. And that's because this is a 1-to-1 function. That idea works with logs as well. So if we have a log graph, let's say we're working with log base 2 of x. Okay, the 0.42 is on log base. Log base 2 of x. Okay, so if this point is on log base 2 of x, if I were to tell you that the output is 2, then you could guarantee me that the x has to be 4. Is there any other point on this graph that gives you an output of 2? No, the only x that gives me an output of 2 is 4. So if we were working on a problem, let's make that another example. If we were working on a problem and we had log base 2 of x equals log base 2 of 4. Okay, so if we have log base 2 of x equals log base 2 of 4, use your intuition. Don't think real hard about properties and all complicated stuff right now. If log base 2 of x equals log base 2 of 4, what does x have to be? It has to be 4. That's the only way these two are going to be equal to each other. And that's true. That's what this property says. But the reason this property works is because log is a 1-to-1 function. Because this input has exactly one output and this output has exactly one input. And once again, that's only because the function is 1-to-1. Because if we take something like x squared is not 1-to-1. Fails the horizontal line test. So let me ask you this. Change of plans. Ignore that example I wrote. Okay. If the output is 9, then what did I plug in? You're not sure, right? That's the thing. Because this is not 1-to-1, you might have plugged in 3 or you might have plugged in -3. So just because you know the output doesn't mean you know for sure what I put in. I mean, there's only 2 choices here, but you don't know for sure which one I put in because this output has 2 different inputs, right? So that part is a little wordy, is a little complicated, and you don't have to stress about it. What you just need to realize is if you're solving an equation like this, then you can just equate the exponents. And if you're solving an equation like this, you can just equate the stuff inside. That's what you need to know here. The explanation of why those properties work is something we need to do in Precalc and Rich, and hopefully you got something out of that, but you don't need to stress if it wasn't completely clear. Even if we were in class together, it's a tricky thing to fully grasp. But the benefit of the video is you can watch it again if you would like to. Okay, 2 more properties to go. Okay, here's our next property. For our next property, if you have a log where you have a base and the expression inside is the same base but raised to a power, basically everything's going to cross out and just leave you with whatever that power was. So here are some examples. See how that base matches the base for the expression inside? Basically what's going to happen here is everything's going to cross out and just leave you with that exponent. So here, because that base matches this guy inside, everything's going to cross out and leave you with the exponent. This one as well, because natural log is log base e. You can just end up with a 4 there. So this, once again, is a nice shortcut. But you don't actually have to memorize that property because you can always solve these on your own. Let's look at this example. If you wanted to solve log base 5 of 5 to the 6th, you already know how to do that. You could do 5 to what power, because that's your base, that's your exponent, equals the other guy. And if you have 5 to some power equals 5 to the 6th, what does that missing exponent have to be? It has to be 6. And what property did you just use? You just used this one-to-one property. It's so intuitive. It comes so naturally to you that if these are equal to each other, the exponent has to be 6, that you use that property without even realizing it. Okay, so you don't actually have to memorize this as a new property. You can always rearrange to exponential form and solve these. But it's worth seeing also because there's another explanation for this that is kind of cool. And the other explanation for this deals with inverse functions. So here's another justification for the property. So one way I can justify this answer is to switch you over to exponential form, and that should make sense and look familiar. Another way to justify this is to remember some properties of inverse functions. So I'm going to use log base a of x as f, and f inverse is a to the x. And that's where we started the whole chapter. The inverse of an exponential function is a logarithmic function. So these are indeed inverses of each other. And if you look up here, this is a composition of inverses. Which one is the inner function? Is the inner function log or exponential? This is the inner function right here, the exponential. So what this is f of f inverse. So f inverse is a to the x. And if I want to find f of a to the x, then I want to go up here to f, and anywhere I see an x, replace it with a to the x. Okay, so instead of x, I put a to the x. And since this is a composition of inverses, if we remember back to chapter 1, this means that those are going to cancel out and leave you with whatever you're putting inside. So in this case, x. So I think that's pretty cool. Once again, this is like bonus info. So if you are appreciating this other alternate justification and you're like, wow, that's really cool. I can't believe that just came back out of nowhere. Then that's great. But if you're looking at this and you're like, I'm a little frightened right now, don't be. Because once again, you can solve these problems without knowing this property. Okay, so take a look. Let me take you back here one more time. All right, so no stress. If you had to evaluate natural log of e to the 4th and you did not recognize that it was this situation or you didn't memorize this property, no big deal. You're solving this equation. So you know this is log base e of e to the 4th equals some power. If you identify your base, e, the exponent over here, and set it equal to the other guy, you can conclude that e equals 4, that the exponent, the missing exponent equals 4, and you're all set. Okay? So hopefully if you were a little nervous about mastering the entire explanation here, you don't need to be. You can still solve this without being fully aware of those properties. And here's our last one. Our last property today says if you have a base raised to the power that's a log with the same base, once again, they cancel each other out and you left with whatever's inside. So if you have 4 to the log base 4 of x, these are going to kind of cancel out, leave you with x. If you have 3 to the log base 3 of 2, these will kind of cancel out and leave you with 2. And I don't know why I picked 2 again here, but I did. This is 10 to the log base 10 because that's common log. So this is 10 to the log base 10, even though I didn't write the base of 2. And those are going to kind of cancel each other out and leave you with 2. And to explain this property, which honestly you don't see too often, but if you're going to a calc next year, every once in a while this pops up. So you want to be aware of it. An explanation for this, you can go back to your inverse functions that we just discussed. This right here is a composition of inverses again. If you look right here, there's an inner and an outer function. Which one is the inner function? Which one is inside? Log is the inner function. It's inside the exponential. So what this one is, this is f inverse of f of x for the way that I've labeled them up here. So to justify this property, it's f inverse of f of x. And from the way that I labeled them, f of x is log base a of x, so I'm going to replace that. And then f inverse of log base a of x tells us to go to f inverse. And instead of x, put log base a of x. So if f inverse is a to whatever my input is, this will be a to this power. And by properties of inverses, no matter which composition you do, if you have inverse functions, they should cancel out and leave you with whatever's inside. So what's inside here is x. So that's a justification for why this property works. There is another justification as well, but I don't want to show that in the video today. If anyone's interested in the other justification, let me know. I can always make a short video and send it out to you. And that concludes the video for today. And you will be getting plenty of practice on all these skills in the upcoming days. Thank you.